Thermodynamics practice problems from chapter 24, and deals a lot with the efficiency of heat engines and the fact that you can never get more work out of an engine than you put into it, and so you can't get more heat out of one either. So we're going to use a formula that's very similar to the percent error formula, and we're going to take the temperature where it's hot minus the temperature where it's cold, so TH minus TC, and then you're going to divide that by the temperature where it's hot. Now make sure all this is done in Kelvin. So we're going to take the 1500 K, that's the temperature where it's hot, subtract from that the 500 K, that's the temperature where it's cold, divide that by the temperature where it's hot again, which is 1500 K, and when you do that, you end up, oh, you got to multiply by 100, I'm sorry about that, you end up getting 66 point, we'll round up 7% efficiency. So you're losing about 1/3 of the heat out of that. If you come down here, sorry, I forgot to erase this. Come down here, you got to make sure that you do all of these problems in Kelvin. Well, if you notice, I gave it the temperatures in Celsius here. So the very first one, even though you can do change in temperature in Celsius and keep it there, I'm going to go ahead and change it anyway. So if you remember, you had to add 273 to all the Celsius temperatures. So I'm going to take 1273, it's 1000 plus 273, minus, because it's a change in temperature, 473, it's 273 plus the 200 here. Okay? Get that answer and divide it by 1273 again. Multiply the whole thing by 100, and you end up getting 62.8% efficiency for that one. Now this one we're going to go to is a machine that really can't exist because it can't get all the heat to come out of an engine. And but sometimes we can pretend or use a model called an adiabatic process. And it's one where there is no heat flow in or out of a system. So that means heat's not going to flow from hot to cold or come out of that system. And so whenever you have an adiabatic system, you're going to have absolutely zero Q. You got to remember, delta Q means heat. So if there's no heat flow, delta Q would always mean or be equal to 0. Let's come down to this next question there. It says 1,350 joules of work are done on an adiabatic engine. What is the change in internal energy? Well, I don't know why they use this, but for the internal energy, they use the letter U. So the way I remember that is the internal energy is the energy that's inside of a U. So therefore, the formula for it's going to be U equals Q plus W. So Q is going to be the amount of heat that you put into the system. So if you add heat, naturally your internal energy is going to go up. The W is going to be the work done on the system. So if you do work on the system, the internal energy is going to go up. So I got now U equals Q plus W. Well, you got to remember it's an adiabatic system, which means there's no work done or no heat can go in or out. So I'm going to put in a 0 in for Q. And it says 1,350 joules of work are done on the system. So that's a positive 1,350. So the internal energy is going to go up 1,350 joules. Let me move the screen on up. Be right back with you. Okay, on this next one, you got to be really careful of the words. So you're going to read this really carefully here. It says how much work can be done by a gas engine if it's changing the internal energy, which is U, and the heat loss to the outside, which is going to be Q, and you're trying to find W. So I'm going to use this formula that we wrote down up here of U equals Q plus W. Now W is what I'm trying to find. Now look really closely because it says the work done by a gas engine, not on it. So if it's done by it, see where this one up here it says the work done on the system? Well, that means the work done on a system would be positive. If it's done by the system, that means that this W is eventually going to be negative. So just keep that in mind, at the end it's going to be negative. Now, a few more things about this. It says how much work is done by a gas engine if the change in internal energy is negative 1,000. Well, when the gas explodes, you get a real big change in temperature, and all of a sudden that temperature lowers when the piston goes down and does its work. And so therefore the change in internal energy is going to be a negative 1,000 joules. So I'm going to put a negative in here. Once again, the internal energy is going out of the engine once the piston has done its work on it. We'll show you the gasoline engine tomorrow. We'll take the engine apart. Now, the other thing is, it says the heat loss to the outside. This is the heat loss. Well, if you look right up here, the heat transferred to the system is positive. So both of these are positive. Well, the heat lost by the system then must be negative. So this must be a negative 200 joules that I'm going to put in for Q. And now we're going to figure out what W is. So if you subtract both sides here, you end up equaling 800 joules, because if you add 200 to both sides, but that's not a positive 800 joules, that's a negative 800 joules, because the work is done by the engine. It's not done on the system. Be really, really, really careful. It's so confusing when you get into this on the system and to the system and all that stuff. Okay? Finally, we're going to do the change in entropy, and entropy is just so hard for me to understand. It's basically energy that can't be used anymore. So for instance, the heat that comes out of your tailpipe on your car, it's just wasted energy. So it's what we call entropy. It can't be used anymore by any useful work. So why they use this particular letter S for entropy, I don't know. And so once again, since entropy just sucks, it's everything that just sort of goes out and it's not useful anymore, we're going to use an S, I guess. I don't know what they use it for. Now, the formula for it's pretty cool, pretty easy though. It's going to be the energy or the heat change, Q, let's make that a delta, divided by the temperature at which it happens. So if you notice in this equation though, it tells you the entropy of 10 grams of water heated at 0 degrees Celsius, and it goes down to ice at 0 degrees Celsius. Well, they don't tell me what the Q is, but I do know it's changing phase from liquid water to ice. Well, remember when we did that? When we did a phase change, we used the formula MLF. And so I'm going to use the 10 grams of water that I used times the latent heat of fusion, which was 80 calories. And so that gave me a delta Q here of 800 calories that were going to be used just to turn the, or come out just to turn the water into ice. So for my delta Q, I'm going to put in, once again, MLF over T. Don't have to do all this again if you already did it. I'm going to put in the 10 grams. The latent heat of fusion is 80 calories per gram, degrees Celsius. And then the temperature that this was done at was 0 degrees. Now, you got to remember, I can't use 0 because this is the reason why, because I'd be dividing by 0. So you have to add 273 to get that to Kelvin. All these things must be done in Kelvin. And so that ends up being 800 divided by 273. And that's going to give you a total of 2.93 calories per gram degrees Celsius over Kelvin. Okay? I think most of the time you don't use the latent heat of fusion in calories. I think most of the time you change that to joules per Kelvin. So you use a different latent heat. But for right now, if you just keep it in that units, we're in good shape. So that's how much energy cannot be used anymore. The next two things, I'm actually going to do demonstrations in class. I'll have a little power plant here, or a generator that's powered by steam, so you can see a light burn. But I want you to understand how this works. Chemical energy that we burn in coal or natural gas is burned to make thermal energy. So you make it really, really hot. That thermal energy turns a boiler. So that makes steam, and that steam then turns a turbine. So you go from heat energy to mechanical energy. The turbine then turns a generator, and that makes electrical energy. And so once again, we'll show you how that works with the demonstration in class. You take coal, you burn the coal to make thermal energy. Thermal energy in the boils water in a boiler to make steam. The steam turns a turbine to make mechanical energy, which then turns a generator to make electricity. And lastly, we're going to take apart a car engine and also a lawnmower engine. And what I want you to notice there is that the spark plug is going to ignite the gasoline inside the cylinder. So you got chemical changing thermal energy. That heat's going to expand and push down a piston. So that's going to change it into mechanical energy. Then the piston's going to turn your crankshaft, and that's going to turn the wheels. And then the gas gets pushed back out the exhaust pipe. So just make sure you got all those notes down, and that way you don't have to take notes while you're watching the demonstrations. Hope this helps. Hope you have a great day, and we'll see you soon. Love you. Bye.